Let's consider the problem that we didn't finish from the last video. I'd like to find the equation of the tangent line to the folium of Descartes, x cubed plus y cubed is equal to 6xy at the ordered pair 3, 3. Now, because this is a relation and not a function, we're going to begin by immediately differentiating both sides with respect to x. Now, once again, we are going to assume that y is a function of x. Even if y is not a function of x, we can still come up with a domain restriction that is going to restrict, well, yeah, that's what a restriction is. That's going to restrict the domain to make this a function. As such, this assumption is always okay to make. Now, given that we're differentiating with respect to x, that means we're going to be treating x as though it's our independent variable. We're going to be treating any y as though it's a dependent variable or simply another function. So if we had, for example, a composition of functions like y cubed, the chain rule would be necessary in a situation like that. Allow me to explain. The derivative with respect to x of x cubed is very straightforward power rule. It is simply 3x squared. Whereas if we differentiate with respect to x, and the variable is different, like y cubed, we would still apply the power rule to the outside function, but then the inside function is y. The chain rule says after we differentiate the outside function, we differentiate the inside function as well. That would be the derivative of y with respect to x, which we'll simply refer to as dy over dx. On the right-hand side, 6 is a constant multiple, which is why I'm going to ignore it for the time being. X times y would be considered a product rule derivative. So that'll be the first times the derivative of the second. Once again, we're differentiating with respect to x, so the derivative of y would be dy over dx. This would be plus the second times the derivative of the first. Derivative of x with respect to x would be 1. What I'm going to do is distribute on the right-hand side, and then make the observation now that we have dy dx occurring on both sides of the equation. I am, however, interested in solving for dy dx. So I'm going to bring this term over to this side by subtracting, and I'm going to bring this term over to this side by subtracting, giving us 3y squared times dy dx minus 6x times dy dx is equal to 6y minus 3x squared. I'm then going to factor out a dy dx as though it is a greatest common factor, leaving us with 3y squared minus 6x. That'll still be equal to 6y minus 3x squared. To finish this off, I'm going to divide both sides by the coefficient of dy over dx. And that'll give us a nice fraction over here on the right-hand side. Now, technically, I believe this fraction could be reduced if we factored out a 3 from the top and bottom and reduced it. However, to take us back to the original problem, all that we're looking for is the equation of a tangent line at an ordered pair. So what I'm going to do instead is go ahead and plug in the given point. So the notation that we'll use, this will be dy over dx evaluated at the ordered pair 3, 3. This will be 6 times 3 minus 3 times 3 squared all over 3 times 3 squared minus 6 times 3. Simplifying the numerator, you're going to get negative 9, and simplifying the denominator, you'll get positive 9. Negative 9 divided by positive 9 will simplify to be negative 1. So next up, we now know that the slope of our tangent line is equal to negative 1, and we have the ordered pair 3, 3. We're going to take those and plug them into point slope form of a line. That would be y minus y1 is equal to m times x minus x1, and simplify this as much as possible. We're going to distribute the negative 1 and then add 3 to both sides to get slope-intercept form of our final answer. This will be y is equal to negative x plus 6. This is the equation of the tangent line to the folium of Descartes at the ordered pair 3, 3.